Hello, everyone, and thank you for attending today's webinar, Sustainable WAN Transformation with 800GE Routing, sponsored by Juniper. Before we begin, I will cover a few housekeeping items. On the left-hand side of your screen is the Q&A. If you have any questions during the webcast, please type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience consoles are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow help widget. Here, you can find answers to common questions. A copy of today's slide deck is available for download in the blue resource list widget. Near the end of today's presentation, please take 1 minute to complete the survey that's open on your screen. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Sterling Perrin, Senior Principal Analyst, Heavy Reading. Sterling?
Thank you, Barbara, and hello, welcome everybody to Sustainable WAN Transformation with 800GE Routing, sponsored by Juniper. My name is Sterling Perrin, and I will be the host and moderator for today's webinar, and I'm joined by two expert speakers from Juniper to walk us through today's content. I'll introduce them here. Of course, you'll hear from them quite a bit as we go through. First, Amit Bhardwaj, VP Product Management with the Automated WAN Group within Juniper. Hi, Amit. Welcome.
Hello, everyone. Thanks for joining today.
Looking forward to your talk. And Amit will be helped by Dwayne McIntosh, Director of Product Marketing, also in the Automated WAN Group with Juniper. Hi, Dwayne. Welcome.
Hi, good morning. Thank you very much for having us.
Yep, looking forward to this. For everybody in the audience, this is a flow of the agenda, market trends and drivers. Dwayne and I will cover that, and then we'll move over to Amit for most of the remaining sections. Silicon systems requirements, converged optical routing, looking at kind of the renaissance of IP over DWDM. On the software side, network automation and programmability. We'll have some conclusions, and then we should have hopefully about 10 minutes for Q&A at the end. So please do ask questions as we go through. We'll gather them up and hit as many as we can live before we close out. So let me start and set the context. 1, 2, 3, 4 slides in. So AI, we need to talk about AI. Clearly a huge driver for a lot of what's going on in the communications industry right now. So the AI revolution was seemingly launched with the OpenAI's ChatGPT, which kind of took over the world in 2020. But it really did begin a couple of years prior to that with the introduction of transformer models, which is what ChatGPT and many others are based. GPT is generative pre-trained transformer, so that's the T in any of these models that we're seeing that have T in the name are transformer. They enable the natural language processing that we're seeing, and all of the explosive growth that we're seeing in AI. From an analyst or from an industry analyst perspective, looking at communications, the ins and outs of how these models work themselves is well beyond my expertise. But so we're looking at, well, how do these affect the network? And it really starts with the computational demands that these new models are placing on compute. And that's what the left-hand chart shows. This comes from NVIDIA. Jensen Huang just presented an updated version of this at their conference in March, but this pretty much shows that trend. If you look on that left line was kind of the trajectory AI was on, how much training compute was required. And it was growing at about a 45-degree angle there, so it's a pretty steep growth. It was training compute demands, in this case, were increasing 8x every in 2 years. So that's pretty significant. But the real explosion was, again, these transformer models, including ChatGPT, which is that purple line, which is growing almost vertically. And that is really the AI evolution that we're talking about right now. The requirements increased 275x in 2 years' time. So just incredible demands on the network. So what does that mean? It's driving massive compute, and Jensen Huang talked about this in his keynote. XPU units, whether they're GPUs, TPUs, the tensor processing units, or CPUs, massive compute, and then the interconnect for all of that. And the interconnect includes within the chip itself, chip to chip, within the rack, connectivity connecting racks, and then connectivity in the data center that's connecting these AI clusters together. We're seeing a massive growth and interest, hyperscalers ramping up in their connectivity between the racks and the clusters, moving to 800 gig in 2024. Immediate demand for that, and then at conferences around the world, we're certainly seeing a lot of interest in R&D going towards a path to 1.6T and even 3.2T, so that there cannot be enough connectivity between these systems and networks within the data center itself. Connectivity and between the racks and clusters, it's largely optics-based, and the focus, there's a very strong focus here on lowest power consumption within the data center. So for folks that were at OFC, all of the talk about linear drive pluggable optics, LPO, and co-packaged optics, or CPO, this is all aimed at driving capacity and reducing power as much as possible. That's all within the data center itself. So what happens in the wide area network, which is really the focus of what we're going to talk about today? We know that traffic within the data center drives traffic between the data centers. This is the data center interconnect opportunity. It's been growing very strongly for many years. And we know that when we move to 800 gig for data center interconnect, at 800 gig, DCI is going to be the #1 driver for moving to 800 gig in the wide area network. The chart on the right here comes from Omdia. Also, I should have said the chart on the right on the last slide is also from my colleagues at Omdia, who are graciously letting me share some of their data from forecast. So this particular one here shows high-speed coherent pluggable shipments through 2028. So this is share of coherent pluggables. And so what the difference between the data center and between the data centers is the move to coherent pluggable optics for the distance. These are many, many kilometers, whereas data center side, we're talking about tens of meters, 100 meters, et cetera. So while 400 gig in data center interconnect is going to be the primary interface and is currently what operators are standardizing on, 800 gig is going to grow sharply, and so as a share of total high-speed units, we're going to see a sharp increase of 800 gig share through 2028. Again, 400 gig is going to continue to grow in terms of its units, but 800 gig has a strong uptake even through 2028. DCI is, as I said, the #1 driver. It's a big one, but it's not just about DCI. We're also going to see 800 gig adopted in long haul and core networks. These are also standardizing on 400 gig today, but operators in our surveys and heavy reading surveys tell us that they want and need a path to 800 gig in the future. One of the aspects of the coherent pluggables coming out that support 800 gig that may be overlooked is that they can also run lower rates other than 800 gig, particularly 400 gig. And for these long haul types of applications, there's an interest in dialing down the modulation. So moving to a lower order modulation over these newest generation pluggables, running them at 400 gig to get you basically 400 gig anywhere, any terrestrial network really in the world, and the ability to even do a lot of subsea applications. The other application or use case I'll call out, and Amit will talk in detail about all of these, but router to router peering within the data center. So this is a WAN application, but the actual implementation of this is connecting routers within the data center to peer, basically ISP to ISP. And we're going to see a migration to 800 gig for that as well. So those will be routers, which we'll talk a lot about today with an 800 gig interface on them. Beyond scale, so scale and capacity is critical, as we've just talked about, but there's a number of other priorities as operators look at their systems and as they look at on a network basis. Reducing power consumption is critical. The lowest watts per bit is increasingly a crucial metric across all service provider types. There's a very acute issue within the data center that's driving this LPO and CPO deployments. But even in the wide area with coherent optics being used, there's a strong focus on reducing power within the optics and within those systems themselves. It relates to sustainability, which has been a topic. It also is key for profitability because power is a huge component of overall OpEx within an operator. And as we look at telecom specifically, we're kind of in a tough space between the early adoptions and rollouts of 5G and then coming 6G, where there's going to be a very strong focus on reducing costs for the network. So huge driver, which gets me to the next points on CapEx and OpEx. Very strong focus. Any architectures that help drive lower OpEx and CapEx are going to be very well received and needed by telecom operators specifically over the next couple of years. IP over DWDM is an architecture that does exactly that. This is the integration of optics on routers. It started with 400 gig for a number of reasons we've talked about on past webinars, but it cannot only be relegated to 400 gig. Operators need to know that IP over DWDM is also going to be viable at 800 gig, as well as beyond. The chart on the right comes from a heavy reading survey we did last year of network operators globally, and primarily telecom operators in this case. And I put it here just to show that operators really want to move to this type of architecture. The top one here, so over the next 3 years, 65% of these operators saying they want to move to coherent pluggable optics on switches and routers. That's IP over DWDM, and it's actually stronger adoption than the coherent pluggables that they're looking at for any other type of network element. So very real trend. One operator at OFC just recently told me that a very large operator said IP over DWDM is inevitable for their network. Other points I'll make, and then bring in Dwayne to kind of expand on some of the key trends. But I do want to talk about automation. Again, we're talking about network level. So on the software side, machine learning as well as AI itself is going to help network operators reduce their OpEx specifically. So a lot of interest in that coming through in our surveys, as well as security and reliability. Not just important, but as we survey operators 1 year to the next, the requirements for security and reliability are actually becoming higher from year to year. So there's a lot of asks and requirements, capacity, but in a way that's done to reduce CapEx, OpEx, increase security, reliability. It's quite a set of requirements. Folks like Juniper are building the networks that are going to make that happen. So with that, let me actually, before we bring in Dwayne, let me go to our first poll question, and then I'll bring in Dwayne to expand on some of the trends. So, we talked about adoption of 800 gig E in the wide area. It's brand new. This stuff will start to ship this year. Curious for you as the audience, what either your plans are if you're a network operator, or what your customers' plans are if you are selling into service providers. And we've got a number of options here. Just pick the one that fits best, and I'll push them out once we get to a critical mass. Deploying this year, so as soon as available. Planning deployments next year, 2025, kind of would be what we see in our forecast, the initial ramps over the next 2 to 3 years. Or are you in a position where you're evaluating, but no plans currently? Or if 800 gig is kind of pie in the sky for you, not under consideration at all. So those are the options. Let me just wait a second here, and let me push, and then I may update, but let me give it this push here. And Dwayne, let me bring you to comment on what we're seeing.
Sure.
Yeah.
Right. I think this makes a lot of sense. We certainly are seeing customers today who have 800 gig requirements, core peering, data center interconnect, certainly data center implementations where our routers are being used in close architectures for spine and leaf roles in the data center for AI. And I think from majority of accounts, they would at least say they want to future-proof their acquisitions, their purchases to support 800 gig because they know it's an eventuality. So I think we certainly see about a third of the accounts deploying today in whatever capacity, planning next year and evaluating the 800 gig technology as well. And then those that are planning to migrate within the next 2 to 3 years or make sure that their purchases will support that transition. Make sense?
Yeah, yeah, absolutely. Future-proof is definitely a word we're hearing a lot. Let me push this along, and I'll let you go from here, Dwayne.
I'll just
Sure,
make one
so-
comment, Dwayne, before
Sure.
you start.
Oh,
I think that the
Sorry.
survey is exactly what we are hearing from the customers in many one-on-one conversations, especially as it gets to some of the hyperscale use cases like core, DCI, even aggregation in some cases. So with that, Dwayne, to you, very encouraging numbers from that survey.
All right, great.
Right. So to reinforce that, there are a number of diverse factors that are influencing, WAN transformations towards 800 gig. Of course, we all know that year-over-year growth for internet traffic is huge. That's dominated by video content with higher and higher definition type content, dominating like 80% of the traffic generally today. Managed services is even rising with SD-WAN, SASE. Managed service offerings are growing substantially at a 32% CAGR. And then we see a huge market growth in data center interconnect. And then notwithstanding all of that, of course, is AI traffic explosion. So for AI data center deployments, for back-end systems, as well as front-end inference deployments, huge growth in model development there, where we see 4x related traffic growth like every 2 years. So across the WAN as well as within the data center, we see that 800 gig requirements are very strong today for implementations today or future-proofing their networks to support it in the next year, 2 years as they migrate. So it's really crucial to have 800 gig capabilities to alleviate these network pressure points. Traditionally, we talk about core peering as being some of the first areas to increase throughput efficiency requirements. We talk about data center interconnect becoming, again, a dominant use case where 800 gig is required. But as you can see here, we're hearing requirements or future-proof requirements for 800 gig requirements in access and aggregation, like in the cloud metro, and in edge networks for multi-service edge functionality, as well, of course, as in data center fabric, where spine leaf architectures, close architectures that are implemented are getting higher and higher demands from the higher processor GPUs, like from NVIDIA and the like. So, at the end of the day, there's really 3 main pillars of requirements that we see in these environments when you support 800 gig. Clearly, performance, right? Adapting to 800 gig bandwidth expansion, as required. So accounts don't do this overnight. It's incremental. So they have to support their legacy 100, 400 gig interfaces and continue to grow. So it can be done organically as the demand occurs. As you mentioned, sustainability. Sustainability is really key. Sustainable efficiencies from your silicon, from your systems, from how you do automation and engineer your network on the fly with, say, SDN. It's critical that power efficiency, space efficiency, your carbon footprint can be lowered. And then automation. So security, operating your environment efficiently at 800 gig speeds is no small endeavor. So as we implement MACsec encryption, as we automate these environments, we want to make sure that The functionality integrates easily into your existing operations environment, and we can enhance that with service visibility. So our blueprint for this WAN transformation then kind of falls in these three pillars. So from an automation perspective, Juniper has Paragon Automation. We have capabilities to look at the service level, so we can see what the service experience is from the customer. So we focus on their experience and are they getting their service levels that are required. Open management APIs and protocols are critical, and that these are driven by open outcomes-based type models. So whether it's NetConf, Yang, telemetry, we want to be able to fit into these environments in a standard open way. From a performance perspective, of course, support for all the use cases we just discussed as they evolve in fixed and modular form factors. Our Express 5 ASICs, again, is a top performer, 7 nanometer technology we'll get into here in a second, but that really enables us to support 800 gig and beyond and provide the efficiency that we're looking for in these environments with coherent or non-coherent optics. And then the last point here is on sustainability. We really look at sustainability from a multi-layer efficiency perspective. There's sustainability you gain within your silicon that you develop. We have custom silicon with Express 5. Our systems are energy efficient chassis. They're designed to be as energy efficient as possible. And then operationally, we support green traffic engineering functions like with SDN to lower our costs overall. So this is basically an overview of our blueprint. I'm going to hand it over to Amit to drill down a little further on this. Thanks.
Oops, I clicked one more. Thank you, Dwayne and Sterling, for talking about the big trends. I'm going to go the other way. I'm going to start with the basics, okay? And then we'll talk about the more complex things. We'll go to silicon, we'll go to systems, and we'll talk about security and automation. So let's go to the fundamental thing. I mean, many of you said you are going to do 800 gig very soon. But there's one thing which is really, really important is 800 gig. I say 800 gig, and then I'll go to 800 gig. 800 gig itself brings a lot of new things to the table. Let's start with 800 gig. So what does 800 gig bring to the table? For sure, it brings an 800 gig port. So that means instead of doing 2x400 gig, you can do single port of 800 gig and reduce the amount of link aggregation and get more efficiency in the network. But 800 gig, like Sterling was also mentioning earlier, brings IP over DWDM to the table. You know, I remember when 400 gig IP over DWDM started to get mainstream, many customers said, will it happen in the 800 generation? Will it happen in the 1.6T generation? The answer is yes. It's absolutely happening in 800 gig, and we believe it'll happen in 1.6T and 3.2T also. So IP over DWDM is one of the most sustainable trends that will continue. Then AI ML is driving adoption of 800 gig in the data centers, right? The NICs, the NICs from the AI clusters, and then all the architectures behind that is going to get optimized with 800 gig over the next 3-4 years, which means these clusters can't just sit in one single data center. They have to span across data centers, and that'll drive the demand for 800 gig in the DCI to go across the data centers also. And over time, that goes into the core networks, you know, into the peering networks, and it percolates everywhere, you know, from a technology standpoint. The second thing, as we go to 400 gig, 800 gig actually brings a lot more when we talk about 400 gig, because number one, it doubles the 400 gig density, right? So every 800 gig port can be used as a 2x400 gig. And this 2x400 gig is not just a breakout. This 2x400 gig, in this case, is using dual LC connectors. So you can get, you know, 2 400 gig literal ports from every 800 gig slot in there. We talked about IP over DWDM. Again, as we go to 400 gig with these same 800 gig ZR optics, you can go do long haul and ultra long haul use cases at, you know, 50% of power capacity, of power efficiency. So lots to bring in the table for 400 gig. And similarly, on the 100 gig, it doubles the density, but at a much better power footprint, right? So a lot of things that 800 gig brings to the table, and we believe that the customers will use these for all these different speeds and feeds. And we did this, showcase this in OFC this year, where we had our PTX 10002 with 100 gig, 400 gig, 2x400 gig, and 800 gig and 800 gig ZR ports all running at the same time in the 10002 router. So this is real. Next thing I want to talk about from the ports is go to the silicon, right? Before I go to silicon, a brief commentary why silicon is important. There was a time, I would say, before COVID when people started to talk about good enough, right? But really what happened was good enough was pretty poor because people don't think about good enough. Good enough means, just do the basic stuff. But the reality is, the silicon is becoming more and more important, not just to networking, across the board. You look across the board, right? Apple's doing their own silicon. All the AI is driven, discussions are driven through Silicon Fest. Networking is the same. We believe silicon plays a huge part here from optimizing the networks for the today and for the future. And when we go up to the 800 gig generation, the first question is, okay, what does the silicon should look like, right? And we talk about silicon, the first thing we talk about is the throughput. What is the right radix for the silicon? If you're doing 800 gig ports, and the magical number tends to be, okay, can I do 36 ports on the chassis line card? Can I do 36 ports on the fixed modular form factor? You multiply 36 by 800, the magical number is 28.8 terabit silicon, right? And using some of the chiplet technology here, like you see in this picture, there are two chiplets here which are connected with short reach SerDes, and they basically two chiplets behave like a single piece of silicon. It's exactly what you heard from some of the AI ML presentations of late. Cutting edge technology from a silicon perspective. And we can take these two chiplets from a fixed form factor, for example, and into the chassis line cards, and we can put these two chiplets onto the line card and do 28.8 terabit line card. So that drives really the power efficiency of the systems from that perspective. And second, no limitations. No limitations means that you're doing 28.8T, every port 800 gig port should be capable of doing 8 by 100, 2 by 400, and 1 by 800. So that's important from a silicon perspective. And not just do that, but do that in a more secure way, which means maxsec at line rate for all speeds and feeds and all ports. And once you do that, you can start to enable some of the hyperscale use cases. So we talk about hyperscale use cases like all the use cases mentioned here: core, peering, DCI, DCH, aggregation, AI network. These use cases will continue to drive the growth in the bandwidth for many, many years. But what is critical to address these use cases also is some of the capabilities the silicon needs to have, right? For example, from a scale perspective, can I support the FIB for V4, V6 scale, not just for today, but for next 10 years, right? Because in the peering networks, the V4, V6 just continues to grow. So state of the art now on this silicon is about 20 million plus FIB. For the core use case, can I do the number of tunnels that's required in the core? Can I do 100K plus tunnels, for example, right? So that's important from the silicon capability perspective. Then we start to go into some of the other hyperscale use cases, like aggregation, where multicast is important. So protocols like Beer will simplify multicast, right? Hercal QS is becoming important, not just in the aggregation, but we're also starting to see in the DC use cases where customers want more than 8 queues when it comes to DCI applications. Visibility into the networks, right? The telemetry inline. The memory can be fungible, so you can do scale for different applications depending on what the resource requirements are. Security for things like peering. And scale in general, saying the scale it's not just about driving the scale from filters, from ACLs, from sampling rates, but also doing that without a performance hit. And we've done sometimes in the past, some benchmarks with other things, and realized that it's not easy. Doing scale without a performance hit is something we pride at Juniper. I think this is an important part to look at when we look at the silicon that you want to build in your networks or deploy in your networks today and the future. So that brings me to the systems, right? You get your silicon and you try to understand what the silicon can do. and then we start to build the systems. And in this case, it's about the fixed form factors and the chassis-based systems. And you drive the industry-leading throughput and efficiency, because the state of the art now, because of the faceplate, is about 20 to 36 ports, both in the fixed form factor as well as the chassis-based systems. Having that single chip really drives the efficiencies from a power and space perspective. And no limitations across the board, not just for the client optics, but also for the coherent optics. So every port is capable of doing 800 gig IP over DWDM. As we go to 800 gig, there is also 400 gig, which is deployed today and still being deployed. And 400 gig will be deployed for next 10 years. It's never going to go away. So what's important is that there is backwards compatibility. For example, if you're putting a line card, 800 gig line card on the chassis, it should be backwards compatible with the current 400 gig line card. It should be backwards compatible without changing the fabric and with the new fabrics. So you get the full flexibility how you introduce 800 gig into your network. And finally, with these big systems, it's not just the silicon, it's also the control plane. So the combination of the silicon and the control plane drives the scale. Scale, for the routes, for the convergence, for the sampling, and all the things we talked about on the previous slide. So now let me take a step back, or take a step higher, and go to the use cases, right? And now we start to look at the hyperscale use cases. And in these hyperscale use cases, there are certain things that are important. For example, in the core, it's important you have scale from a BGP perspective, scale from a tunnel perspective, the scale that makes your core networks fully secure. Take another example of peering. Here we're talking about v4, v6 scale. We're talking about the fact that, can you do DDoS filtering at scale without a performance hit? We go to the AI networking. Here, the large radix devices have started to become really important, because you can really take the large radix chassis devices in the spine role in this AI ML clusters and reduce the 5-stage class to a 3-stage class. And the value for that is, you start to eliminate actually a lot of optics from the stage 3, from the 5, as you go from the 5-stage to 3-stage, and also it drives a better power footprint, because now you're using much fewer devices in the network. And we keep going on the other use cases like DCI, DC Edge, and metro aggregation, where VPNs start to become important, because you have multiple customers in this scenario, and isolating those customers in a multi-tenancy situation in the data center, but same thing in the metro aggregation with L2, L3 VPNs, EVPNs, and advanced QoS capabilities with hierarchical QoS. So when you get a silicon that drives all these use cases for the hyperscale, I believe this is really useful for the customers, because you could take one tool and use it in many different use cases, because that's less certification, less qualification, and also driving advantages from a sparing perspective. So with that, Sterling, let me pass it to you for one more survey question.
Yes, thank you. So this one, we wanted to get into the use cases. So Amit, great job going through the different use cases that are kind of on the table as operators move to 800 gigs. So we want to hear from you, the audience, on which use cases are the top requirements for 800 gig. And in this one, it's actually choose all that applies. So you can select, hopefully you can select multiple. And he's kind of walked through them all, but core, peering, data center interconnect, or data center edge, but the things around connecting data centers, core and edge, metro, all the data center interconnect options there. Metro aggregation, or AI, which is the intra data center application. And let me give it a moment. Maybe, Amit, I'll put you on the spot here as we wait them out. What would your top 2 be? What do you think are the top 2 that are going to come in? And then I'll push out and see how it goes.
My top 2 are going to come in as core, and DCI, and I would say
Okay.
3 AI networking clusters.
Yeah. All right, so you gave 3. Let me push him here. We're about 40% of the audience. We'll give it a shot. Core, DCI. So yeah, so DCI in all its forms, top by a fair amount, then core, and then for this audience, the AI, a bit less, although this is a WAN webinar, so take that.
Yes, that's fair.
But yeah, any other thoughts or comments on this?
Very interesting to see the metro aggregation numbers. That's
Yeah.
like almost a third of people think metro aggregation would be one of the interesting use cases. And I agree, because as we look at the densification of metros with the 5G, yes, and 5G becoming more virtual, this starts to make sense, because now you're not just doing aggregation, it's basically a data center sitting in the metro.
Yeah, good point, Amit. I mean, I kind of glossed over metro aggregation myself. I was a bit, thinking that's a bit longer term, but maybe these results are saying I should look at that a bit more seriously in the future. So yeah, always good stuff from these polls. Let me push to the next one in the interest of time, and I believe you're still up, right?
Yes, I'm still up. Thank you. Okay, so like we said, as we go to the 800 gig generation, and we did some numbers on our side, what is the value going to be from a sustainability standpoint? And all these numbers are well vetted out by Juniper with our products. For example, clearly, I mean, it's simple. You double the density in the same space. You get 50% space efficiency with 800 gig solutions. For the silicon, we're going to see at least 49% improvement of watts per gig. But silicon is only just one part of this, because as you get this efficiency on the silicon, there are other things that take power, like the fans and all that stuff. And those fans start to become more efficient as the silicon power goes down. So we're starting to see, for example, on a PTX 10002, driving 75% power efficiency as compared to the previous generation. And we'll start to see the same thing on the modular form factors. Also, we don't have the numbers for modular form factors yet. We're still measuring them, but just from an ASIC perspective, we know it drives 77% efficiency when you take all the silicon and forwarding silicon, as well as the silicon that goes into the fabric. But that's not all. We can take all this stuff, because we have these platforms which are capable of doing a lot, but we can also turn off a lot of stuff which is not being used. And we can also optimize the network based on how the network is being used, and drive even more savings with capacity optimization with Juniper Paragon driving 27% on top of everything that's on the left. So I do believe we are moving to a world where things start to get more sustainable, and we're going to use a lot of automation tooling to make it even better. One of the technologies, my favorites, I know it's one of Sterling's favorite too, is IP over DWDM. You see different naming for this. We at Juniper call this CORA, Converged Optical Routing Architecture. What this brings to the table as compared to the previous generation is that it used to be, it still is there is routing and there is transponders, right? These are two different things like ships in the night. And we've been trying to do multi-layer for so long, but it's really complex to do when you have IP layer, which is actually quite, standards-based, but you have the optical layer, which is actually quite proprietary implementations from all the optical vendors. As we go to IP over DWDM, but every routing port is capable of supporting DWDM. This wasn't the case in the past, but it's definitely the case in 400 gig generation. It's the case in the 800 gig, and will be the same in 1.6T and future. This is where everything is heading from a IP over DWDM perspective. So as we get there, we start to merge DWDM onto the routers. We eliminate one control plane completely. We got so much, simplicity now in the network. We also start to make things more efficient, because it used to be that you had extra capacity being provisioned on the optical side, extra capacity on the routing side. Now we can just do the planning at a single layer and really, really optimize things across the network. And some of the numbers at the bottom that you can see, we did these numbers, taking a transponder in a router and putting DWDM optic on the router. We start to see 54% the power savings 77% space savings, and 55% carbon footprint savings. I think the value proposition is pretty significant. And let me just demystify this in a very, very quick way. Like, what does 800 gig IP over DWDM brings to the table? A lot right now, because literally you can use this 800 gig ZR optics and build any terrestrial network without using any transponder. So there's some reaches mentioned here, like 800 gig for metro applications going up to 500 kilometers. Then you can start trading speed with distance. You want to go longer, like long haul or regional, 1,000 kilometers, you can go to 600 gig with the same optic. And you can go to ultra long haul applications at 400 gig exactly with the same optic. So now you can use the same optic, same routing platforms, and deploy any terrestrial network with IP over DWDM in the 800 gig generation. And that brings me to take a step. Let's just treat the whole router as a black box. What does that mean? And the question really is, when you have a black box, how do you automate that black box? My favorite example sometimes is Tesla, which is, we have a car now which drives telemetry and everything can be programmed on the car. So routing is basically the same. Everything can be programmed, right? Because we provide those, we build that stuff in the hardware for programming, and everything all the data can be streamed out from the routing platforms. So this is the commitment we have. From a standardization perspective, it's good to have standardized models, and this is why we are continuing to invest in open config. But we also know that the standard models, they're getting better, but they're not complete yet. So we have native data models and the standard-based models to drive the programmability of the platforms. And then we look at from a telemetry perspective, we got to use some of the standard, services, gRPC services. So all the telemetry can be ingested by, a Paragon automation, or it could be open source collectors, or customers' own collectors for collecting the data from the network. And we just launched things like Telemetry Explorer and a Yang Data Model Explorer, where as the code is written for providing the telemetry and the Yang models, it can be exported to an online tool where customers, the programmers, can look at this tool and see what is available in what release from a telemetry and Yang models perspective. Now, if you have programmers who are trying to automate the networks, that's the tool to go to, because you really don't need to know what routing is, because for the programmers, really, I need to know how to program it. I need to know what data to ingest to run my AI models and closed loop automation. And this is exactly what we're using to bring some of these outcomes from a Juniper Paragon suite perspective. You will see Paragon slides. I don't have too many Paragon slides here, but if you see Paragon slides, you will see Paragon has the capability to do all the things from a lifecycle perspective. It starts with planning, starts with device onboarding, service provisioning, optimization, AI ops with ingesting all the data from the network. But in the end, the question is, what are the outcomes that are important for customers, right? We do all this functionality, but we also want to measure the outcomes with Paragon. And some of the things that we're measuring, the outcomes are listed on this slide. For example, can we onboard the devices quickly? Most of the times when the devices are deployed, the people who rack and stack stuff are not the guys who are experts. So can we automate that after the racking and stacking to onboard the device onto the network? Can we go to zero unplanned outages? This is driven by things like active assurance. So every device in the network can be a sensor, which is actively looking at things in the network and making decisions before failure even occurs. So this is an important aspect. And once you have active assurance, you can do a lot more things than just proactive monitoring, but also when things fail and go back into service, you can actually look at that if things are working before you put those things back into the service. So a lot of capabilities can come to the table. With autonomous capacity automation, most of the networks, the changes in the networks are not very frequent. You make the changes, you provision the networks. 90% of the time, the automation tools are going to work to do optimization, right? And this is where the goal here is to optimize the resources based on the usage, because most networks will have different usage during the day and the night, and based on that, you can turn on and off things, and then go to green networking. The green networking has multiple things. I can turn on and off things based on the usage, right? I can also route things through the most power optimized parts of the network, right? For example, if some devices are running at 70% work throughput, some other devices are running at 20% throughput, it's actually better to move that traffic to the 20%, because now overall footprint of network footprint of, the power footprint of the network can go down. So a lot of outcomes it can be driven here, but in the end, the goal is to simplify things, to move things faster, and to drive efficiencies from a both optimization perspective and from a power management perspective. And coming to one of the last bullets that Starling had about security, I think we can all agree that security is fundamental to the networks, right? Security is fundamental to any part of the business today, and we know cybersecurity is top of mind for everybody, every CIO, every CTO in the world. When it comes to the networking infrastructure, the routers are not always sitting in a controlled facility. Many times they're sitting in a third-party facility, in a colo, in a place you actually don't control things. Hence, the infrastructure security really becomes important, which means having things like TPM 2.0, which means your router hardware is coming from the right vendor, which means the software is not tampered. So it's important to have those capabilities from a security perspective. Once you do that, then you start securing your line, which is okay. Any data that goes out of a router can encrypt it, and line rate MACsec becomes critical there. Now we have secured the infrastructure, we have secured the line. There are still vulnerabilities, right? Because the traffic that's coming in is kept sometimes with the malicious attacks. It can drive DDoS attacks. So here, two things come to the rescue. One, when these attacks are happening, can you detect them fast, right? That's number one, which means the sampling rates from the networks are going to be important. Number two, once those attacks are detected, can you actually provision the network really, really fast to prevent those? That's where fast provisioning of the filters is really, really important. And number three, can you actually be very specific here? Because in these filters, we're not just looking at 5-tuple. Can I look deeper into the payload and prevent that malicious traffic? So answer is yes. This is where we're heading with Express 5 and with the platform architecture to full hardware security, MACsec encryption, and a fully secure, from a DDoS attacks, preventing the DDoS attacks perspective. And with that, I'm going to come to my final 2 slides. Dwayne talked about this a little bit, so I may just talk about this. So we announced our 800 gig generation platforms, both fixed form factor and for the modular chassis. You've seen some of these already at OFC and Mobile World Congress. If you're one of the customers, you already have it in your labs. We are driving 28.8 terabits on the fixed form factor and 28.8 terabit per line card on the modular chassis with 3 form factors, 4-slot, 8-slot, and 16-slot. And on the modular chassis, the new line cards are backwards compatible with the current 400 gig line cards. You can upgrade without changing the fabric. You can upgrade with changing the fabric, in which case we'll get the full throughput of the new line cards. The scale and capabilities that we talked about in terms of FIB, tunnels, Heroku QoS, everything is going to be available on these platforms. And we are very, very excited about this, and very excited to see, the survey results where most of the customers are looking to move towards 800 gig. But at the same time, 400 gig is going to be there for a long, long time, and this interop is super, super important. Like I said, these are some of the customers we have been working with, and they've these are the publicly referenceable customers, but there are a large set of customers which is not in this list. So I don't want you to feel bad because this is something we can't public reference unless we have agreement with you. 400 gig has been deployed very widely already. We at Juniper are leading this transition, and we have word of confidence from customers that 800 gig is going to be critical for them, and this 400 gig and 800 gig interop is going to be critical for them, and we'll have to continue to working with you to make this happen in a sustainable, automated, and secure way. So that was my last slide, Sterling. Let's go back to you and see what questions we might have.
Yep, absolutely. Thank you. Thanks both, Dwayne and Amit. And we do have, well done on timing. We got about 10 minutes left. So we do have a couple of questions in, but for the audience, if you have questions, now's the time to fire them away and we'll see what we can address here in the time left. Let me start with the comments, or your comments, Amit, about no limitations in the 800 gig implementation. Looks like they're just looking to understand what the industry limitations are around 800 gig right now. So is it kind of like, I don't know, maybe a litmus test or something, like, just to explain what, I guess, what no limitations means and I guess what it doesn't.
Yeah, thanks, Sterling. So like, I think one of the slides, it said, what does 800 gig bring to the table, right? So 800 gig brings to the table 800 gig, 800 gig IP over DWDM, 2x400, 8x100, and also 10 gig, but let's stick to the higher rates. It's important that every port is capable of doing all of them, because we do see sometimes people talk about 800 gig, but they don't support 800 gig. You know what that means is you're not going to do IP over DWDM efficiently if you don't support 800 gig in every port. We do see sometimes people talk about 400 gig, 2x400 gig, but they're really not able to support the two LC connectors, which means you can still do 2x400 gig, but with not the right connectors from a 400 gig perspective. And then we start to see some folks talk about limitations, like what ports can you do IP over DWDM versus not. So I think those are some of the limitations I was talking about. It's really, really good to not have those limitations. So you get the full flexibility and take the advantage of 800 gig for all the value proposition that 800 gig brings to the table.
Great. Yeah, thanks. Yeah, I had a question myself, but we've got, let me hold off on me. We'll get these in and then see if it comes up. Yeah, maybe this one. Again, this one's looking at the silicon comments, and somebody's interested in how do you support mixed mode operation, both 400 and 800 gig interfaces concurrently?
Okay, thanks. So this goes back to the design of the silicon. So the silicon is designed where we have, this is basically 100 gig SerDes technology as we go to 800 gig. So every port has 8 by 100 gig SerDes routed to it, and using that, we can drive through a software configuration 800 gig ePort, because with 8 by 100 gig SerDes, we can drive 2 by 400 gig, and with the max behind that to do 2 ports of 100 gig. And similarly, we can do for 100 gig because of the way the silicon, the SerDes technology in the silicon itself is designed, allows to do the mixed mode of 400 gig and 800 gig, and every port is individually configurable without any impact from how the other port is configured.
Makes sense. So the 100 gig, sir. Yeah, I mean, at OFC, there was a lot of talk about moving to 200 gig for very specific within the data center. Kind of, I don't know if off topic, but just curious how that, thinking out loud, how that relates to what you're doing with a product that's addressing the WAN applications. Will would you actually reduce some of the flexibility moving to 200 gig SerDes, or is it even roadmap issue as far as Juniper is concerned?
We are committed to 1.60. Let's say, what does 200 gig SerDes bring to the table? 200 gig SerDes will bring 1.6 to the table.
Yeah.
We are committed to 1.60. Without divulging all the details, there will be an express silicon that will drive that transition. And again, same thing. Important as we go to 1.60, not to have the same limitations. So you have silicon that's designed for all the port speeds and feeds for 200 gig SerDes. And similarly, as we go from 800 gig to 1.6T, we follow the same concepts as industry without any limitations again.
Yep, great. Another question came in. Actually, before I do that, let me just remind, there should be a brief survey that pops up for the audience. Just if you could please fill that out before we close out. We do gather up and use that feedback to help with our webinars. This question, and Dwayne, feel free to weigh in as well. This one, how important is interoperability for 800 gig optical interfaces for metro and for regional reach? A big question I get asked as well. Maybe Amit, if you want to start with that, and Dwayne, if you have some thoughts as well.
I think let's see, what does interoperability mean, right? So interoperability means, let's start with 400 gig before we even go to 800 gig. In the 400 gig, as an industry, we drove the standardization to 400 gig ZR, ZR plus, and ZR plus 0 dBm, right? And what that means is that I can have a Juniper 400 gig optic on one side, and I can have a third-party 400 gig optic on the other side, and you don't have to think about it if these will interop on the line. As long as you're using the standard modes, they will interop, right? And that's important because otherwise you get into very bespoke scenarios, and it may or may not work, in the field. Same thing goes to 800 gig. Is that standardization of these modes is important, and what that gives us is in the 800 gig generation is the same thing, a peace of mind that your operations teams does not have to think about, is this interoperable or not? And I believe this is very important because some vendors might look at proprietary modes and stuff like that. I think that mostly adds things for complexity's sake. And honestly, those proprietary modes end up taking more power than it's required for the application. So if you ask me, I think interoperability is something, the biggest goal that we need to adapt in the industry. And if there are some special things that are required, let's make it interoperable.
Yeah, I totally agree. And I think a couple of weeks ago we had OFC 24, and OIF and EA both had a tremendous number of demonstrations, multi-vendor environments with coherent optics, 400, 800 gig coherent optics from multiple vendors that were in our PTX 10002 that we just announced that we showed you today. And it worked beautifully. They were all standard compliant, and even 800 gig 0 dBm solutions were demonstrated. So it was exciting to see, and I think the last couple of years we've seen, that demonstration, and boy, I think we had 11 or 12 different coherent optics vendors plugged into our router, and we showed interoperability, and it's the flexibility for CMES support as well as there. So really exciting how fast the market's moving, and how the standards bodies have really helped to create this type of interoperability that I think at the end of the day the customers win.
Yeah, glad you mentioned the OIF demo, Dwayne. I did a video with the OIF and with Juniper, and that should be out soon. So on exactly that, the massive amount of interoperability demonstrated around the coherent optics specifically in that case. Great. We are at the top of the hour, so we'll close out here. But I want to thank, of course, Dwayne and Amit and Juniper for sponsoring and presenting, and thank you to the audience for attending. and for your questions. Thank you, everybody, and have a great day. Bye.
Thank you. Thank you.
Thank
everyone.
you. Take
Thank you,
care.
Sterling.